In this lecture, I will be discussing linear and time-invariant systems, or LTI. LTI is a title given to a class of systems that respond in a certain way when subjected to an arbitrary input. All LTI systems have the following defining properties. These are homogeneity, superposition, which is also referred to as additivity, and time invariance. You might not be too familiar with any or all of these words, but don't let that discourage you, because the concept of LTI is actually very simple. I'll provide a mathematical description of each and show an example on how we use the property. We'll start with the two criteria that describe linearity, homogeneity, and superposition. Let's say you have an LTI system, represented here in block diagram form, and you subject it to an arbitrary input x of t, and it produces output y of t. Homogeneity states that if you scale the input by factor a, then the output would be scaled by the same factor. For example, if you doubled the input, then the output would also double. Here, graphically, we can see that for this system, if we subjected it to a step input of 1, the output happens to be a sinusoid with amplitude 1. And likewise, if we subjected it to a step input of 2, the output would also double to amplitude 2. Now let's say that the input x1 produces output y1, and input x2 produces output y2. Then superposition, or additivity, states that if you add the two inputs together, x1 plus x2, then the output would also be the superposition of the two separate outputs, y1 plus y2. Sometimes homogeneity and superposition are combined to state that if the input is scaled and summed, then the output will also be scaled and summed by the same amount. If this system meets these two criteria, this is called a linear system. Time invariance refers to the system behaving the same regardless of when in time an action takes place. For example, if you send a slinky down the stairs, the toy will behave the same regardless of whether it's 5 o'clock or 6 o'clock. This can be written mathematically by saying that an input of x of t minus a produces an output of y of t minus a. Or in other words, two similar inputs translated in time will produce the same output also translated in time. Sometimes time invariance is referred to by a more generic term called translation invariance, which also covers translation in space as well. So these three restrictions are all that needs to be met in order to have an LTI system. However, these restrictions on a system are very severe. So severe, in fact, that practically no real-world system fully meets them. There's always some aspect of nonlinearity or time variance in the real world. So that begs the question, why are LTI systems important? I think Richard Feynman stated it best when he said, linear systems are important because we can solve them. That is to say, we have an entire arsenal of mathematical tools that are designed for and capable of solving complex linear systems, whereas we can only solve very simple and contrived non-LTI systems. But equally important to being able to solve them is that a wide range of physical systems can be approximated very accurately by an LTI model, and this is very powerful indeed. For example, LTI systems can be characterized by its response to an impulse function. I'll go over this fully in the lecture on transfer functions, but now I'll explain it briefly just so you can appreciate the power of LTI systems. If you impart an impulse onto a system, such as hitting a mass that is sitting on a table with a hammer, which would send the mass moving along with an instantaneous velocity, and then you observe the response, we would say this is the impulse response of the system. And if there was friction between the mass and the table, then the response might look something like this. Because of the principle of time invariance, we know that if we hit the mass with a hammer at time 0, and then we hit it again at time 1, we can expect the same response at both times. Also, because of the principle of homogeneity, we know that if we hit the mass twice as hard, then we would expect a response that was twice as large. And now, finally, because of the principle of superposition, the full response of the system would just be the summation of both signals. In this case, it's the thick yellow line. So you can see that this method works easily with one or two impulses. But what if we have an input into the system that wasn't just made up of one or two discrete impulses, but was a continuous ramp? And further, if we broke that ramp into a series of sequential impulses, then with an LTI system, we can say that the output is the summation of the responses to each of those individual impulses. Now, for the sake of this lecture, I drew these impulses very discreetly. In practice, each of these impulses would be infinitely close to each other, and the height would be infinitesimally small. So when you added it up, you would have the time response of the system. And when you do this summation in the time domain, this is called convolution, which can be a very difficult integration. However, if we first transform the impulse response and the input signal to the S domain using the Laplace transform, then convolution becomes multiplication. Now this is the basis behind transfer functions and why in the S domain they are only applicable to LTI systems. So how can we take advantage of this knowledge? As a controls engineer, you'll be responsible for designing the controller. That's probably obvious. But what you might also be responsible for is creating the requirements to which a different group will build the sensors and actuators in the plant. Or you might be responsible for choosing commercially made control system elements. Or even, if you're lucky, actually get to design and build your own sensors and actuators. In each of these cases, it is almost always beneficial to design components close enough to being LTI that the non-LTI behavior can be ignored. Or to put it another way, to design hardware that can be modeled as an LTI system so that the standard mathematical tools, such as transfer functions, can be used to design and tune the controller with as little error as possible. Let me leave you with a common example of a nonlinear spring. If you plotted a real spring's stretched length versus its restoring force, it would most likely have a shape similar to this. When you stretched it too far, eventually the material will give and start to deform elastically. If you compress it too far, the coils will start bunching up and physically impact each other. Somewhere in between, in what could be considered the operating region of the spring, there will be a nice, nearly linear relationship between force and distance. If you were selecting a spring for your project, you might specify the region of linearity, that is the range of forces that the spring will likely see, and how linear that region needs to be. So hopefully you have a better understanding of what an LTI system is and why they're so important to designing a control system. Future lectures will show how to linearize a nonlinear system and how to recognize and deal with time invariance. Once again, thanks for following along with this lecture. If you have any questions or comments, please leave them below and I'll try to get to them. And also feel free to leave suggestions for future lessons.